Hello everyone, welcome to my channel. If you're new to this channel or you have not yet subscribed, please support my channel by subscribing and inviting friends to subscribe. Like and share videos on this channel. Your support is much appreciated. If you have already subscribed, many thanks for your support. Now, in the previous video, I did look at evaluation of limits and I went through the first 7 limits. In this video, I would like to go through the next 3. That's from the 8th up to the 10th limit. So let's start. Our first one, like I said, number 8 in this case, it's the limit as x approaches infinity of the natural log of x all over x. Now, if you let x approach infinity here, you'll notice that the numerator becomes infinity and the denominator also becomes infinity. So we have a form of infinity over infinity, which requires us to use what we call L'Hopital's rule. So let's look at our first one then. On page 1, we have number 8, which is the limit as x approaches infinity of the natural log of x all over x, like so. Now, like I said, if you let x approach infinity, the numerator becomes infinity and the denominator also becomes infinity. So we have a form of infinity all over infinity. Now, when you have that form, you need to use what we call L'Hopital's rule. So, which basically says you must differentiate the numerator and then differentiate the denominator, then take the limit. So this is going to be equal to the limit as x approaches infinity of differentiating the numerator. Remember, derivative of the natural log. If I take a separate page here, if you are required to differentiate, for example, the derivative with respect to x of the natural log of x, like so. Basically, it says you must reciprocate x, 1 over x, then multiply by the derivative with respect to x of what? Of x. Now, what is this? This is 1 over x times the derivative with respect to x of x is 1. And what is this? This is just 1 over x. Right. So, basically, that's what we're applying here. Derivative of the natural log of x, we must reciprocate natural log of x and then multiply by the derivative of x. Notice that reciprocate natural log of x like so, 1 over natural log of x times the derivative of natural log of x. Remember, we're differentiating this natural log. So differentiating the first natural log is going to be reciprocation of this multiplied by derivative of this. Now we have to say times derivative with respect to x of the natural log of x. This one inside there now. And we're saying all over, what's the derivative of x? 1. Now, this is going to be limit as x approaches infinity, of 1 over natural log of x. Derivative of natural log of x, like I explained, is going to be times 1 over natural log 1 over x times derivative of x, which is 1. And we're saying all over 1, which is just basically this one here. So simplifying this is going to be limit as x approaches infinity of 1 over x times natural log of x. Now, as x approaches infinity, you will notice that this is just going to be 0 because 1 over infinity is actually 0. So that's our limit number 1 in this video, which is our limit number 8 if you consider the previous video. Let's look at our next limit, which is in this case limit number 9. There it is. The limit as x approaches 0 of e to the power x plus x all to the power 1 over x. Now, if you put x, substitute 0 into the place of x, this is going to be e to the power x, which is e power 0, and that will be 1 plus 0 is 1. 1 over 0 is infinity. So that will be a form of 1 to the power infinity, which requires us to use logs first and then L'Hopital's rule. So remember, we're dealing with techniques of evaluating limits here. Number 9, it says limit as x approaches 0 of what? Of e to the power x plus x all to the power 1 over x. like I said, this is the form of 1 to the power infinity. And that form requires us to let this part here be equal to y. So we're going to say let y be equal to e to the power x plus x and all this to the power 1 over x. Now next take natural log on both sides. So this implies natural log of y is equal to the natural log of e to the power x plus x all to the power 1 over x. At this stage, we're going to apply the one of the laws of logs. This specifically law of logs says the following. You take an extra page here. It basically says, and I've quoted this in a couple of previous videos, the natural log of m to the power p is equal to p natural log of m. Now notice this form is actually that form there, which means the p must come and multiply to get this. So we must take 1 over x multiply there in the back. So this what we have now is the following. So we're saying this implies the limit, the natural log of y is equal to 1 over x times the natural log of e to the power x plus x. Now rewriting the right hand side, we have on the left natural log of y equals on the right natural log of e to the power x plus x all over x. Now at this stage we need to take our natural log, our limit as x approaches 0. So we're going to say therefore the limit as x approaches 0 of the natural log of y is going to be equal to the limit as x approaches 0 of the natural log of e to the power x plus x all over x. Now what you do on one side, you do the same on the other side of the equation. So now what we're going to do here is to check if you substitute 0 in that place and that place, this is going to be e to the power 0, which is 1, plus 0 is 1, natural log of 1 is 0, and if you plug in 0 here, it will be 0. So 0 over 0 in determinate form of 0 over 0, it requires us to use L'Hopital's rule on the right hand side, which means we must differentiate the numerator, differentiate the denominator, and then take the limit. So this is going to be, remember we're coming from limit as x approaches 0 of the natural log of y will be equal to the limit as x approaches 0 of what? Of the derivative of the numerator. Remember derivative of log, I've explained in the previous question. You reciprocate the function, so this is going to be 1 all over e to the power x plus x, right? And then derivative of that, multiply that like so. Derivative of this expression is e to the power x plus 1. Remember, derivative of e to the power x is equal to e to the power x. Derivative of x is 1. We're differentiating with respect to x. And then we're saying all over, what's the derivative of x down there is 1. Right. So now let's simplify this. We rewrite it and then simplify it. So I'll come back and complete that bracket here. Let's take, this takes us to page number 3. Page number 3, let's just fix this one before I forget. Page number 3, we simply rewrite this expression. Let me move this one down, right, like that. Rewriting that expression on the right hand side there. On the left, we still remain with limit as x approaches 0 of the natural log of y is going to be equal to limit as x approaches 0 of, open brackets, e to the power x plus 1 all over e to the power x plus x. Now, if we plug in 0, the right hand side simplifies to a number that's very nice to deal with. So this is going to be e to the power 0 plus 1, remember, all over e to the power 0 plus 0. This simplifies to 1 plus 1 all over 1 plus 0. Basically, our answer is 2 over 1, and this is 2. Now, don't forget where we're coming from. We're coming from limit as x approaches 0 of the natural log of y being equal to that. So now we're going to apply the properties of limits. The limit of natural log is the natural log of limit. So this is going to be we take the limit in the natural log. So natural log of, open brackets, limit as x approaches 0 of y equals 2. Remember I told you the limit of the natural log is the natural log of the limit, right? Now, at this stage, I must just remind you of the definition of the natural log. The natural log definition, if we say natural log of r, we are basically saying that this is the same as log base e of r. And so if we have natural log of r is equal to m, we're basically saying this equals m. And the way that we handle this by to convert from a log form to an exponential form is the e must come into that place. The r stays there, the log is gone, the e comes there, and the m becomes a power. So e comes here and m becomes power. So this is what you have: log exponential form and log form. Right, so this is critical in our case here. So we can rewrite this then to the log base e of the limit as x approaches 0 of y is equal to 2. Remember what I explained here? The e must come there, m becomes power. So here, this is taking the place of r. So we're going to say this implies the limit as x approaches 0 of y is equal to e to the power 2. That's how we get rid of the log form. But now remember, y, where we started from here, y is actually this expression. So I'm going to take that expression, put it here, then I've managed to evaluate my limit. So this takes us to page number 4, just to conclude this. So we're basically saying, therefore, the limit as x approaches 0 of y, remember what I told you, y is e to the power x plus x to the power, or that 1 over x. So this is e to the power x plus x, or to the power 1 over x is just equal to e power 2. And that's our final solution, e power 2. That's our final solution. From there, you can see it. Right, now let's move on to our last limit in this video, which is our limit number 11, number 10 actually. I'll come back for limit number 11 and 12 in another video because these are a bit longer, especially this one. A bit longer to evaluate. It takes longer amount of time to evaluate. So let's just focus on this one here, and then we're done in this video. All right. So the limit as x approaches 0 of e to the power 2x minus e power x minus x all over x squared. Now, let me go straight to this. Is now my page, still page 4, and I'm dealing with question number 10. And question number 10 says the limit as x approaches 0 of e to the power 2x minus e to the power x minus x all over x squared. Now, if you plug in 0, this becomes 1 minus 1, 0 minus 0, 0 all over 0 squared is 0. So we have another indeterminate form of 0 over 0. L'Hopital's rule applies. This is going to be limit as x approaches 0 of the denominator differentiation of the derivative of the numerator over derivative of denominator. Differentiating e to the power 2x is just 2 e to the power 2x. Differentiating e to the power x is e to the power x. Differentiating minus x is minus 1. All over derivative of x squared is 2x. If you plug in 0, again, this becomes 2 minus 1 is 1 minus 1, 0, 0 there, 0. So another indeterminate form of 0 over 0. L'Hopital's rule to apply again, this is going to be limit as x approaches 0. Differentiating this, now we have 4 e to the power 2x. This is just minus e to the power x, and that will be minus 0. Derivative of a constant is 0, and minus 1 is a constant. Differentiating 2x, the answer is 2. Now, plugging in 0 in the place of x, you'll notice that this simplifies to 4 e to the power 0, because 2 times 0 is 0, minus e to the power 0, and then 0, we can ignore that, all over 2. And this simplifies to, this is 4 minus 1 all over 2, and our final answer is 3 all over 2. That's our final answer to question number 10 or limit number 10. All right, I'm going to stop here. Like I promised, in my next video, I'm going to just complete these two and perhaps look at many more techniques of evaluating limits. We have not forgotten about integration. We will go back to integration. And like I said, the applications of differential calculus will be next after I'm done with limits and integration, basic principles or techniques of integration. Once I'm done with that, then we'll move to applications. And then I will just move after that, move to other cases of differential calculus, or even move from mathematics all the way to statistics altogether. All right, if you're new to this channel, like I said in the beginning, in the introduction there, support us by subscribing and inviting friends to subscribe. Sharing these videos will help us to build and grow the channel, be able to produce many more videos and support as many students as we possibly can. All right, God bless. See you next time.